Welcome to the next lecture on statistical methods, and it's part of the course on research methods, but we've been working on statistical analysis and working with very basics in statistics. In the last lecture, we worked with the measures of central tendency, which is mean and mode and median, and now we will move into measures of dispersion and looking at how dispersion or what are the deviations in your data set. And the dispersion, by definition, it's the degree of variation in your data. And another key statistics to remember is the word range, and range is the difference between the maximum and the minimum value. Now, why measures of dispersion are important? Well, if you have if you compute the central tendency, such as mean or median, and the next thing to know is how much data varies and how much is the heterogeneity in your data set. To get a clear indication of variance in your data set or variation in your data set, you need to compute some measures of dispersion. And usually the measures of dispersion that we normally compute are called variance and standard deviation. Variance is the square of standard deviation, or put it the other way around. The standard deviation is the the square root of variance. Now, the measures of central tendency present present one aspect of your data, and the measures of dispersion or variance present another aspect of your data set. Now, let me take you back to the same example that we have worked with in the last lecture, where I said that let's say you have 5 students in your class, and those 5 students have attempted an exam or a test, and in that test they obtained five grades. Each and every one of them got a distinct grade, and we computed the average grade for the class, and now we will compute the measures of dispersion for the same students. So if you look at the slide here, you would see that the variance, the formula for the variance for both population and the sample are given, and this time around you will see that the difference between the two formulas is a little bit more than just the one that we saw for average. In fact, these two formulas are different, and the reason they are different is because n is the number of observations for population, but when we compute the variance for a sample, we divide the deviations, the square root of deviations, by n minus 1. That is, we subtract 1 from the total number of observations in our data set. Now, if you focus here for the population, and I'll illustrate how we do it. Let's say we have a data set in which we have n number of observations. N could be 65 or 600. And in those n observations, we have a variable. It could be a grade for the student, and those grades are listed here, which are xi. And then mu is the average or mean of the population. So we subtract each observation. Each observation from its mean, and then take a square. We square that difference, and then we sum up all those square differences. Once we have found the summation, once we've done the summation, we divide that by the number of observations. And this is how we compute the variance in the data set. If you were to take the square root of this statistic, that would be standard deviation. As I mentioned in my last discussion, that more often than not we are working with sample, and in sample we actually do not divide the squared deviations by n, but instead n minus 1. And remember the distinction that in sample the number of observations is denoted by small n, whereas in population the number of observations is denoted by capital N. Similarly, the difference between the mean, we denote the mean for population by mu, and we denote the mean for sample by x bar. Let me illustrate this particular calculation for sample in Maple, which is our computerized calculus. So it's computerized calculus software. Here's the data set. We had 5 observations, and I mentioned that these are the grades obtained by students in a test, which were 45, 66, 88, 75, and 58. When we summed that up, we got 332. We divided it by the number of observations, and we had 5 observations. That came out to be 66.4, and that is our average. Now, in order to compute variance, and let me just say variance, in order to compute variance, we will take the same data and we subtract, and the equation for variance, as I mentioned, is as follows. Let me just write it up here. It's the summation I is equal to 1 and to 5, and we have xi, which is here. Let me type x subscript I minus x bar. Let's just call it. Just take an easier notation. If I can find mu, I would use mu. Let's me just use mu here, and then divided by n, capital N. Let's say here. So basically, if we were dealing with variance of a population, and let me just type it here, variance of a population. The formula I showed you in my in the slides earlier is xi minus mu, and actually this is not correct. We need to square it. So I'll just click here and say square of this, and then I press enter, and basically this is the result. You take the first observation, subtract the mean from it, and then square it and divide it by the number of observations. Then you take the second observation, subtract the mean from it, and then divide it by the number of observations. Now here's our data set, and I can copy this statistic here, bring it down. So 45 is the first observation, 66.4 is the mean, and if I were to take the square of it, and square of this, plus do the same. Second observation was 66. This is the grade obtained by the second student, and I subtracted the mean from it, and we do the same for the third student. Third student got 88, and we subtracted the mean 66.4. The fourth student received 75. We subtracted the mean 66.4, and the fifth student obtained 58, and we subtracted the mean 64. Notice that I've added square with every student, and so basically what we have done is that we have subtracted the mean from each grade, and then after subtracting it, we have squared it, and I press enter, and I get this number 1069, and that is the variance. And if I were to take the square root of this, I can let me just take square root of 1069.2, and this would be the standard deviation. 32.69 would be the standard deviation. And go back to our slides. This is exactly what I did. I took the observation, which is the grade obtained by a student in a test, subtracted the average grade for that class, and then squared it, and then summed up the deviations for all students. That is the difference between what they obtained and the average obtained by the entire class. When I summed up those deviations after squaring them, I divided them by the number of observations, and that's how I got this number, 1069.2. And if I take the square root of this number, 32.6 would be the standard deviation. And that is actually my next slide. That is the same. If you take the square root of it, you get the square root of variance is standard deviation, both for population and sample. Now notice one thing, that in the formula we have n as 1. I could have done the same thing, and I could have taken the n out, and it would have been the same thing. I didn't necessarily have to divide it by n every time. I could have actually taken it as a common element and then divided the square deviations only once by the total number of observations, and it would still be the same thing. So why we take standard deviation? The difference between variance and standard deviation is that the standard deviation is the square root of variance, but standard deviation has an advantage. Standard deviation is in the same units as the observed data or the variable. For instance, if you are working with the grades obtained by students in a particular course, and the average value is 66.4 out of 100, and if you take the variance, then variance would be not in the same units. And see, the variance here is, in this case, 1069.2. When I take the square root of that variance, I get the standard deviation of 32.69, and that 32.69 is actually the same units as the grade. So the average of 66.4 and the standard deviation of 32.69. So why do we compute this variance? The purpose of finding variance, either the variance or standard deviation, is to determine how much dispersion is in our data set. How much dispersion, because when we know the dispersion, we know how much heterogeneity there is, and we can actually compare two populations looking at the variance and standard deviation. Let me give you an example. Let's say you have two different classes, and in two classes you have 40 students in one, and let's say 50 students in another. And let's say that you have you administered the same test to both classes, and let's call one class as A and the other as B. And class A, the average was 65, and class B, the average was 74. However, the standard deviation in class A was 12, whereas standard deviation in class B was 45. So it tells us that in class B we have a very high variance, we have very high and very low values, whereas the average of class A is smaller than the average of class B, but there is much less dispersion in the data set. Now these calculations that I've just shown you by hand, these calculations are, or these algorithms are already coded in R Commander. You can actually select the data set and the variables of choice, and you can compute statistics by yourself by just pointing and clicking. And I will illustrate this by showing you how to do it in R Commander. Now, if you have not started R Commander, you recall that you first have to install start R, and after you have started the R, you type library, and then within parentheses type R Commander, and it will launch the R Commander, and this is the screen that you will see. Now then you would click on data and say load data set, and then locate the data set that you would like to load, and then click on OK. I've already got this data loaded, so I'll just say cancel. And then here on statistics, I can actually summarize the entire data set, and if I click on summaries, statistics, summaries, active data set, the computer tells me that there are 27 variables in this data set, and would I like to proceed with the summary of all. Now this is a small data set, 27 variables, about 200 odd observations, but sometimes you have large data sets with few hundred variables, and computing the summary statistics for few hundred variables may not be very useful, because you cannot simply process all that information in one go. And that's why we only compute the summary statistics for variables that are of immediate interest to us. So in this particular case, we have 27 variables, and I think we can handle those 27 variables. So I will say OK, and I click OK here. Notice in the script window, the computer types summary and then the name of the dataset HDI. This command, summary HDI, summarizes all variables in the dataset. And if I scroll up a little bit, the output window actually is now where the answer lies. And if you look at the HDI.rank, the Human Development Index was created, and then all countries were ranked according to that. And you could see that the minimum value was 1 and the maximum value is 1012. And these are the variables in the data set. Let us pick urban as the variable. Urban stands for percentage of the population that is urban in a particular country. And it's very illustrative here. I have highlighted the variable name urban. And you would notice that the minimum suggests that the minimum urban percentage recorded in our data set on Human Development Index or Human Development Report, it's 11%. So the country with the minimum or the least urban population was the one with 11% of the population as urban. And then if you look at the median value, you would notice that the median is 58%, which implies that half of the observations, or equal number of observations, are above it and equal number of observations are below it. If you look at the mean value, it suggests that the average for the urban population is 56%. So on average, 56% of the population is urban in our data set, and the maximum recorded for urban population is 100, and this is for a country or more than one countries where 100% of the population is urban population. Again, notice that the script window gives you the command that the program executed, software executed. The command was summary, and then the name of the data set, HDI, and then it created this summary value for all the observations. Now, this is meaningful. Now, the percentage of population as urban, it's a continuous variable. Let us see what the software generates for a variable that is discrete or categorical. And one of those variables that was categorical is the Human Development Index, but categorized as very high, high, medium, low, and others. And here's that variable. This is a categorical variable, HDI.cat2. And notice that there is no mean or median or mode or quartiles or reported for this variable. The only thing that is reported for a categorical variable is how many observations are categorized as very high, high, medium, and low. And similarly, we had the GDP variable, the size of the economy, the gross domestic product. We coded it as low and high, and you would notice the only thing that the software is reporting is the number of observations. So it recorded as 174 countries. And we coded it arbitrarily, but that it suggests that 174 countries were coded as low income and high income countries were only 8. But this is an arbitrary categorization that we did just to illustrate that if a variable is categorical, the summary statistics that we compute are frequency counts rather than mean, mode, or median. And when we would like to see more detailed values, if we want to see numerical summaries, and when we are interested in looking at standard deviations, we click on statistics, then summaries, and then numerical summaries. And when we look at numerical summaries, and let's just pick up urban again, and I will just select urban. I just clicked U, and then urban comes up. And I would like to see the mean value, the standard deviation, and I click OK, and here it is. We have 194 observations in our data set, and the average percentage for urban is 56.3. That is that on average 56.3% of the population in our 194 countries are urban, and the standard deviation for those 194 countries is 23.2. The standard deviation and the mean both are in the same units. Mean is in percentages, so 56.3% is the average urbanization on the planet, on the globe, especially for those 194 countries. And the standard deviation for these 194 countries is 23.2%. Again, because we recorded urban as percentage of population urban, both mean and standard deviation would end up in the same units as the one in the observed data set. The next measure that we will be working with is the coefficient of variation. Now, if you were to create a link between a relationship between the measure of central tendency and the measure of dispersion, that would be coefficient of variation. If you take the standard deviation of a data set and divide it by its mean, that gives you the coefficient of variation. It has no dimension, it has no unit, because the standard deviation and the mean are measured in the same units, and when you divide standard deviation and mean both being in the same units, the resulting statistic would be dimensionless. And it's useful when you're comparing data that are scaled differently. To return to the same example in our commander, we have the mean as 56.3 and the standard deviation as 23.25. Now let me return to statistics summaries, and let me have the numerical summaries again computed for urban, but this time around I would compute the mean and standard deviation across the human development index categories. So I select the summarize by groups. I would like to compute the mean and standard deviation, but I would like to summarize them by certain groupings, and I select this categorical variable, which is a factor variable, and I click OK, and I compute the average urbanization across the human development index categories. You will notice that the very highly developed countries are more urban, 77% urban on average, than medium developed countries, which are 46.24%, and then the low developed countries are the least urban, where the average urbanization is 33%. So you can quickly draw some inferences that as countries become more developed, they become more urbanized. The very highly developed countries are much higher urbanized than the low developed countries. So there is sort of a link, a correlation between the state rate of urbanization and the state of the economy, or state of development, human development. Now I would like to compare these means, and also would like to compare the standard deviations. So I can actually do these calculations here. For the very high developed countries, the standard deviation is 17.4, and to compute its coefficient of variation, I would divide the standard deviation by the mean. So the standard deviation is 17.4 and the mean is 77.3, and I compute this, and then I compare this against the low developed countries, where the standard deviation is 13.03, which you could see from the table, divided by the mean value, which is 32.9, and then I select these two commands here. If you are following me, you can select these two commands here, and after selecting those two commands, I click on submit, and look, it has computed these two values for me. The coefficient of variation for very highly developed countries is 0.225, and the coefficient of variation for the low developed countries is 0.39. This allows me to conclude that there is more variance in the data for low developed countries than it is for very highly developed countries. The coefficient of variation is very high, comparatively very high, for low developed countries than it is for very highly developed countries. Another measure of central tendency is the coefficient of skewness. In my own practice, I do not use it very often, but it is a measure of relative symmetry, and it can take any value between -0.5 and 0.5. So -0.5 is the lower limit, and +0.5 is the higher limit. And basically, if the data are symmetric, you would see something on your screen here. This is an example of a symmetric data set. You have a mode in the middle, and then observations are increasing towards mode and then decline afterwards. If you have a positively skewed data, then you would have the bulk of the data towards left, and then it declines. And if you have negatively skewed data, you have very large observations towards the right, and so this is called the coefficient of skewness. And another thing is called kurtosis, and the coefficient of kurtosis is a measurement for peakness, how peaked your data is. And if you have very high peak, then the kurtosis would be high, and if the value is reference value is always 0. If you have the coefficient of kurtosis greater than 1, you have relatively peaked data and small dispersion. But if you have the value less than -1, then you have relatively flat data and you have greater dispersion. So whenever you have very high variance in your data set, the coefficient of kurtosis would be approaching -1 or lower. And if you have very peaked, very highly peaked data and have all the observations are concentrated in a very narrow interval, then the coefficient of kurtosis would be approaching +1. Now, the standard deviation has a relationship with normal distribution as well, and we will discuss normal distribution later in our lecture on distributions. But it is quite possible that you are already familiar with the normal distribution, because often people talk about the bell-shaped curve, and there's an interesting relationship where if the data are normally distributed, then within one standard deviation of the mean value, you would have at least 68% of the observations, which means that 68% of the observations would have a value of either mean +1 standard deviation or a value of mean -1 standard deviation. Now, if we were to go back to our example where we were working with the mean value of 66.4, this is the average grade of those 5 students that we have been discussing, and if the mean is 66.4 and the standard deviation is 32.69, and if the data are normally distributed, what we are saying is that almost 68% of the students would have a grade for that test, which would be either the mean value +1 standard deviation or the mean value -1 standard deviation. So if you plot that interval, you would have at least 68% of the observations. And within the mean +2 standard deviation and the mean -2 standard deviation, that interval would cover almost 95% of the observations, and almost 99.7% of the observations would fall between the mean value and ±3 standard deviation. And if you look at the graphical display, this is what we mean by normal distribution. It is called the bell-shaped curve. If mean is mu, and then within this interval of mean +1 standard deviation and mean -1 standard deviation, in this interval you would have at least 68% of the observations. This interval here would have 68% of the observations, and this interval, which is mean -2 observations and mean +2 observations, this interval would have 95% observations, and the mean ±3 standard deviation would have almost 99.7%. The discussion about fractiles is in order. It is a characteristic that describes the location and spread of data over its range. Within fractiles, the most commonly known are quartiles, that you take the data set and you divide them into 4 quarters. The lowest 25% observations, then 25 to 50%, 50 to 75%, and then 75 to 100%. And these are called quartiles. And the 50% observation is in fact the median, and these quartiles allow you to see how dispersed is the data and where it lies. The other commonly known fractile is the decile, where you take the data set and you divide it into 10 equal categories. So the lowest 10%, then 10 to 20%, and so on and so forth. And the highest decile would be 90% to 100% data set. And the percentile could be a division of a data set into 100 equal parts, and it shows the points below certain k percent of the observations, and k being 18%, 14%, 100%, 45%. So the commonly used fractiles are quartiles and deciles. And if you recall how our commander has been printing some results or publishing some results here, it presents the first quadrant and the third quadrant and the mean and the median. So the median is the 50th percent, and the first quadrant is the 25%, and the third quadrant is the 75% fractile or quartile. Now, there's another way of looking at data, and it's called proportion. And the proportion is basically the fraction of a data that has certain characteristic. If you have a data set with number of students who obtain certain grades, and let's say that if the minimum grade to pass the exam is 70, or then the proportion of students or the number of students who obtain marks higher than 70, and you divide that by the total number of students in the class, you'll get the proportion data. And that proportion would be the proportion of students who actually pass the exam. The next stage of looking at the data is called is where you start looking into the relationship, how two variables relate to each other. Now, up until this point, we have looked at the univariate statistics. The average reports to us the central tendency of one variable. A standard deviation gives us the dispersion within the same variable. In both instances, either it's average or standard deviation. You're simply looking at one variable. But what if we were to be interested in two variables? For instance, if we have data on rainfall, the precipitation levels are recorded on a daily basis, and we also have data on the number of umbrellas sold in the city in a particular day and for every day. Is there a relationship between rainfall and the number of umbrellas sold in the city? Can we assume that if there's more rainfall, we'll probably be seeing a higher sale of umbrellas? Now, to find this relationship between two variables, that type of correlation could be measured by using the correlation coefficient. And the correlation coefficient is basically the covariance between two variables divided by their respective standard deviations. Then the question comes as what is covariance? And the covariance is the average of the products of the deviations of each variable from its mean, and it describes how two variables move together. For instance, if two variables move in the same direction, that is, an increase in one variable results in an increase in the other variable, that would be the case with rainfall and the sale of umbrellas. That is, more rainfall and more umbrellas. But if so, they are moving in the same direction. An increase in one is correlated or is accompanied with an increase in the other one. Now, there could be a case where an increase in one variable is associated with the increase decline in another variable. For example, let's take the example of rainfall. An increase in rainfall may be associated with the decline in attendance in the offices. People see rainfall, they see flooding in the streets, or some other problems, and decide to stay home. So while the rainfall is increasing, the attendance in the offices is declining, and so the two variables are moving in two different directions. So the covariance is computed as follows. You take an observation, you take a variable, or in this case two variables, and you subtract those variables from their averages. And after you've subtracted those variables from their averages, you multiply those two variables for each observation, and you do it multiple times for as many observations as you have. And after doing that, you sum it up. You sum up these deviations and divide it by the number of observations, and that is called the covariance. And if you divide the covariance by the respective standard deviations, you get the correlation coefficient. So on this slide, the covariance is given here. This is the formula for covariance, and this is the formula for correlation coefficient. And I think it would be interesting if we were to do this by hand. Let me just show you one example. I'll use Microsoft Excel. So let us switch to Excel to compute correlations. Now I have here created some dummy data. The data are for GDP per capita expressed in dollars, and life expectancy at birth. So the variable here that you see, these are the 5 hypothetical countries which have GDP per capita of $35,000, $22,000, $12,000, and the lowest is 4,000, and the life expectancy at birth is 80 years, 77 years, 66, and so on and so forth. Now, in order to compute correlation coefficient, which is right here, and I'll put it right up here, I need to first determine the average values for both variables, right? So I computed the average using Excel formula average, and then I highlighted the range C4 to C8, and it gave me the average as 15,800 for GDP per capita. And the average life expectancy at birth, again I typed average and I highlighted the range. You could see that in your screen as the blue color box. This is the average, which is 64.6, or almost 65 years of age. The next thing to do is to subtract the individual variable from their means. So taking the GDP per capita xi minus x bar. So I took the GDP minus the average value of the GDP. So 35,000 minus 15,800 is 19,200. So I got this here, and I did the same for life expectancy, which is 80 for the first observation minus 64.6 is 15.4. Now I repeat this for all the observations, and I have them here. And then once I have got these values here, this is xi minus x bar, and this is yi minus y bar, I have to multiply these two. So I multiply these, and I get this. I call this variable a, and this as b, and I multiply a times b. So this multiplied by this, and I get 295680, and I repeat it for all the observations. And here's the a times b, and then I have to sum it. Remember the summation sign, sigma I is equal to 1 to n being the number of observations, which are 1 to 5. So 1, 2, 3, 4, 5, and I have to sum this multiplication. So I have multiplied these here. I select these and I sum up them here, and this is my sum. And in order to get the standard deviation, and we are assuming that this is the entire population, so I'm not gonna subtract -1. I'll just divide it by n. So when I take this sum and I divide it by n, I get this number, and then I have to further divide it by the two standard deviations, the standard deviation of x and the standard deviation of y, and I have to multiply these. So I've done this here. I've computed the standard deviation. Look at the cell here. The formula for standard deviation, the command is type stdev standard dev, and then highlight the range, and you get the standard deviation in Excel. And I take these values here, and I divide the above, which is the sum of the multiplication of deviations around the mean for the two variables, and then I divide them further by multiplying the two standard deviations, and this gives me the correlation coefficient. Now this looks like a little bit involved computations, even with Excel. Obviously a little more involved if you were to do it with calculator, but that's why we use statistical software, because these algorithms are pre-built. So let me show you how to do this with real data set. We have GDP per capita for 194 countries, and we also have life expectancy at birth in our data set, and I would like to find the correlation for the two. And I will move to our commander. I click on statistics, and I click on summaries, and after clicking on summaries I click on correlation matrix, and I select correlation matrix, and now I have to pick the two variables. So I had the GDP per capita, and I look for that. GDP per capita is right here, and the other one is life expectancy, and I will scroll down. These variables are listed in alphabetical order, and here's the other variable, life expectancy at birth. Now notice that when I click on it, before I click I will press control. I press control and then I clicked on it. This way I have got both variables selected. GDP per capita is selected, and you can see that there's a blue background with white text, and the other variable selected is life expectancy at birth. And I would like to compute the correlation for these. And remember, this time around we have 194 observations. Once I have selected these two, I press OK, and I get this matrix right here where you see the correlation between life expectancy at birth and GDP per capita is 0.615, and this is symmetrical. So what you see here, you will get the same value up here as well. The correlation coefficient is telling us that there is a strong positive correlation between life expectancy at birth and GDP. That is, richer countries have higher life expectancy at birth and poorer countries have lower life expectancy at birth, and the correlation between the two is 0.61. The correlation coefficient could have a value, a smaller value of 0 and a very high value of 1. It moves between the interval of 0 and 1, and weaker correlations would be around 0 and the stronger correlations would be approaching 1, and this appears to be a strong correlation. We can in fact find the statistical significance of this correlation, but that would be slightly advanced at this stage, and we'll do it at a later time. So this is the correlation matrix, and in our slides we go back, return to our slides, and look at the graphical representation of correlation, and I would show it right here. Now look at the left top graphic. This is an indication of positive correlation. There are two variables. One is plotted on x-axis, and you see that if the association between the two is such that if one variable increases, the other one also increases. That is called the positive correlation. In the other graphic on your top right is an example of negative correlation, where one variable is increasing while the other one is declining. So the y bar, this variable suggesting that it is increasing, but the value for the other variable is declining, it's going further south. This is a negative correlation. Again, positive correlation when both variables move in the same direction, negative correlation when variables move in the opposite direction. If there is strong or mild positive correlation, you will get a positive number. A negative correlation will return a negative number, so it could be minus 0.3, minus 0.8. Anytime you have negative correlation, the numbers are the correlation coefficient would return a negative sign. Now there's also this condition where you may not have any correlation. For example, the sale of shoes may not have any correlation with the sale of sugar. Right? If you plot the correlation, you find out that the sale of sugar and sale of shoes is independent. There is no correlation, and in that case, you wouldn't see any trend, which is plotted here in the graphic at the bottom, that with an increase in one variable does not necessarily see either an increase or decline in another variable. So once again, in our commander, you click on statistics, then on summaries, then on correlation matrix. Select the two variables or more. You do not have to have just two variables. You can select as many variables as you want, and then our commander would compute a matrix where the matrix would be symmetrical. It's a square matrix. Here you look at three variables. The same three variables which are reported in the first column are also reported in the first row, and the diagonal would always be 1 because each variable is perfectly correlated with itself, and the off diagonal elements are of interest to us, and the correlation between two variables could be plotted by just drawing a line from here, and this is a positive correlation of 0.58 without worrying about what these variables stand for. This is just an illustration. Now in our commander, you can also determine the statistical significance of that correlation between two variables, and I'm just showing you that this is possible. You have to install load a package called HMISC, and then you can compute these values. However, the point I'm trying to make here is that this is slightly advanced at this stage because we haven't gone through the hypothesis testing and significance levels, which we'll do later, and then probably revisit this later. The only thing to recognize is that if you're trying to determine correlations, you can certainly compute them in Microsoft Excel, but you wouldn't be able to compute the significance level of those correlations. And the reason why significance level is important is because even if you see a weak correlation of 0.2, we still would like to know if this is statistically significant or if it's an insignificant correlation. So as I mentioned that the correlations could be both positive and negative. In order to completely comprehend this concept, let's consider three variables. Percentage of urban population within a country is one variable. The other variable that we were working with is life expectancy at birth. And the third variable is education, but low level of education. The way these variables are coded as if the country has lower education levels, the percentage of adults who have not completed um, basic education, and then those percentage of adults who have completed basic education would be recorded there, and then it's an indication that a large number of population is of low education, and the other variables are self-explanatory: percentage of population that is urban, and life expectancy at birth. Now, we can think of this in the following way. We can assume that life expectancy at birth would be high for countries with higher urban population. And the reason we are making this assumption is because we have seen that more urbanized countries are more well off. They have higher incomes, and this affluence is also associated with longevity, or at least life expectancy at birth. So again, urbanization is tied to higher incomes, and higher incomes are tied to higher living standards, and in turn higher life expectancy at birth. Now, the lower education is a variable that tells us that this country has lower education, and then one would assume that if a large number of population is poorly educated or has lower education, then obviously that country would have not very high income, and then if the income is not high, then probably the life expectancy at birth would not be very high. So let me show you what we can do with this. I will select statistics, summaries, and correlation matrix. And this time around, I'm selecting three variables. The variable urban, and I select urban, and I press Control. And then the other variable is life expectancy at birth. I press Control and click. And the last one is education, and I will select education, and I'm selecting low education. Before I select it, I press Control and then click, and then I press OK. And as soon as I press OK, let me first show you what I've got here. The software quickly produced this syntax, which is saying compute correlation from the dataset HDI, and then this command where the syntax is that it takes a comma and then puts three variables: education, low, life expectancy, and birth and urban, into this syntax, and then another syntax specific command which says use all observations, and this syntax generates the correlation matrix, which I will select in the output window here. Now, as I mentioned, that on the diagonal of this matrix you will always get 1. 1 suggests that each and every variable is correlated perfectly with itself. And now if you look at the correlation between life expectancy at birth and low education, you see that if the percentage of individuals who are poorly educated increase in a country that is more illiterate or more poorly literate individuals, the life expectancy would decline. And the coefficient of correlation between life expectancy at birth and lower levels of education is negative 0.45. Similarly, the correlation between urban and low education is negative, and it's minus 0.25. That suggests that as urbanization increases in one country, in a place, the lower education would decline. That is, more and more would be literate. So urbanization and higher literacy go hand in hand. And the correlation between urbanization and life expectancy as birth is also reported here, 0.64. And this way you see that there's a matrix of 3 by 3, where 3 variables are reported here, and the same are reported on the first row. And you could see that life expectancy is correlated with education and also with urbanization, and you can see that the matrix is symmetric. What you see on either side of the diagonal, you get the same values. So in summary, correlations and covariances and standard deviations, these are all measures. These are all statistics that we use to understand how data varies in our what is the dispersion or the measures of central tendency. But note that means and modes and medians and standard deviations are univariate statistics. They tell us something about one variable, whereas covariances and correlations are multivariate statistics, or at least bivariate statistics, because they can tell a relationship between two different variables. And here we saw that correlation could be both positive and negative. Sometimes two variables move in the same direction, that is, an increase in one variable is correlated with an increase in another variable, and then the resulting correlation is positive. And the correlation coefficient would always move between 0 and 1. It could take a positive or a negative value. A positive coefficient reflects positive association, and a negative coefficient reflects a negative association between two variables. So this concludes our lecture today, and I hope that you will be working with our commander and the HDI data, and would be computing the the measures of central tendency and dispersion, as well as the correlation coefficients. There are 27 plus variables, I think, 27 variables in our data set, and I will encourage you to find the correlations and the average values and the standard deviations for other variables